Yeah.
Okay. Did you start? Wait, did you start?
I did.
Okay. All right. Hi everyone. Okay. So this is our last lecture of the quarter, and it'll be on localization, which you guys probably don't know what it is yet, but we'll go into that. A couple things first. Wait, what? Okay, sorry. Wait, why did it skip a slide? Is this going to be a pattern? Okay, all right, don't worry about it. Okay, so we have a couple of announcements. Lab 2 is due this Wednesday at midnight. I wanted to do a quick progress check, so I don't know. Could we like go around the room starting with Laura? Like, what part have you guys reached?
I haven't had time to start.
Okay, that's and then Roshan, right?
Me too.
Okay, Nishat.
My group hasn't started, but we're planning on doing it tomorrow.
Okay, Solomon, I know you. Yeah, and then I'm sorry, I got it. Gerard.
Yeah, we basically finished part 2. That's
Okay. Okay. Alexis.
Yes, I'm part 3 right now.
Okay, Anthony.
Also part 3.
Okay, Ryan.
Where are we? Part 1.
Like.
Like, we just finished part 1.
Okay, that's honestly, it's like not even as bad as I thought. Hi guys. Actually, could I ask, how far have you guys made it in Lab 2?
Nearing part 2,
Okay.
end of part 3.
Okay, so what do you think? Like, should we? What's up? We need a work session. When? Like, you mean for Lab 2? Yeah, I mean, I agree. But like, when can we put it?
33% completion rate.
Okay, why don't we just? Okay. Like, for those of you guys who like aren't completed, like, do you anticipate like many hours going forward, or like what are you guys' thoughts? Like.
Sorry?
Yes.
Okay. Okay. All right. So we were thinking of giving like a general extension on the due date, especially because like a lot of the time that we gave you was basically dysfunctional because you guys had midterms and stuff like that. So I don't know, like we can like say like next Tuesday, and then like if you guys are asking for an extension, it's gonna ruin your Thanksgiving break, so you should probably get it done by then, right? Do you think that's like a good idea? Next Tuesday? Okay. All right. So we're gonna go ahead and codify that, I guess. So we are changing your Lab 2 due date to next Tuesday. No. Okay, so I mean, obviously you guys are still like allowed to like request extensions and stuff like that, but like I don't know, just think of this as an extension already in some ways, because we will be releasing Lab 3, and then we don't want you guys to fall behind catching up on labs and stuff like that. So just try to get Lab 2 done as quickly as you can. It'll be beneficial in the long run. Second announcement. Oh yes.
When is Lab 3 due?
Lab 3. Pretty much at the end of the quarter is the rough idea. Yeah. Right. End of the quarter. Yeah. Okay. So yeah, it'll be on the Lab 3 spec, which will probably come out like next 2-3 days. Okay. Second announcement. GB applications, they've been extended, so they're now due Tuesday. This is like a great way to get involved in the club beyond pocket racers. Also, if you're looking to be on board next year, it's like a great way to get involved with a lot of officers early and stuff like that. So I don't know if you guys have IEEE ambitions, it'd be highly recommended to join a GB. It's in the announcements on Discord. There's like a lot more information there, but like here's 2 links, I suppose. Work session 3, we had it scheduled for like the Sunday after Thanksgiving, but if I'm gonna be honest, like that's not a good idea, so we're gonna move that. Any thoughts? So like if we put a work session on a weekday, like what do you guys even think about that? Like it's probably a terrible idea, right?
What weekday?
Okay, let's say we did like a work session on like Wednesday night.
That's chill.
Like
Yeah.
how
5 hours and then work session.
Oh, well, no, that doesn't work. We have an officer meeting. Okay.
We just displace officer meeting.
I don't think that's a good. Okay, like Thursday?
I can't Thursday.
I can't Thursday.
Okay. Yeah, I figure Monday, Wednesdays, because you guys are here on a Monday, right? So like Monday, Wednesdays are fine, but Thursdays are nice. And then Micromouse has the Monday taken.
Should we not do Sunday like after we come back? Like as in like
Again. Yeah, we were thinking about that, but like also,
that's like week 10.
or
Better than
yeah, okay.
everything else. I would opt for me.
Yeah, okay. I kind of agree because we've been doing Sundays, so I think people.
Week 10 work session, guys.
Okay.
Thoughts?
It's the Sunday leading into week 10.
Yeah.
Oh,
Yeah. Okay. I think that's reasonable.
could be worse.
That lab is not going to be as like annoying as the second lab.
Okay.
So, because the dice lab is like kind of better, right? Okay. And then last announcement is your kids have received like a camera mount and a camera now. You don't really have to do anything about that currently, but that's something you will need for the next lab. So we've, you know, there's already instructions in the lab specs and stuff like that for you guys regarding this. So you don't need to worry about the fourth announcement for now. Okay, moving on to the actual content. So for your next lab, basically what will happen is you'll be given a dice and you'll be asked to count the number of dots on that dice using OpenCV, which is an image processing library. So this is just like a, I don't know, like introductory slide. So we have here like a picture of slide 6 dice, white dice, black dots, and then we apply some image filtering, and then we get to the second image, which also has like, I don't know if you can really see, but the white dots are circled, and then there's a count, 6, which is correct. So you'll be building towards this in your third lab. So what is localization, right? It's basically just finding things. I guess a local comes from like the fact that you're finding things on like a local level. Yeah. Okay, so the problem with finding things is humans just look at an image, you know, and then they see like certain aspects of it. But when we pass an image into a computer, it's really just like an array of numbers, which we've shown there, right? There can be 3 numbers representing like red, green, blue, and then they're in like a, you know, like a X by Y, like width by height, like massive array. So it's pretty much like incomprehensible as far as the computer is concerned. So we need to like properly apply some techniques. So one of the problems actually is that like all that data, it's really hard to read. Like even like like your cameras probably take like photos on the order of like megabyte scale. That's like a lot of pixels. So computers will really struggle with dealing with that. And typically we're only interested in certain aspects of the image. So we don't actually really need all that data. The other thing that might be confusing for computers is like separating out visual noise. Like we humans as like the product of like evolution are very able to like, you know, pick out like certain attributes in an image and stuff like that. It's not necessarily easy for a computer. So we're gonna explore all sorts of techniques in a way to like help the computer start finding things out about images. So what tools do we have? I think 1 or 2 people are gonna moan and groan about this one, but we have convolution. Okay, so this slide is titled Remember Convolution, but I think a lot of you guys are experiencing it currently. So convolution is basically the process of taking like 2 images and like, or sorry, not 2 images, 2 functions and then convolving them. That is to say like flipping and dragging one of the signals over the other signal. So we have like a little diagram of that shown here. So this is something that's covered primarily in EE 102. And fortunately for you guys, we're not really going to delve too much deeply into this like time domain convolution because it's not super relevant to us. What's moving towards like a sort of more relevant direction is this one, the discrete convolution formula. So has anyone here taken EE 113? Okay, I didn't think so. So 113 follows 102, and it's basically talking about the subjects of 102 like convolution in a discrete form. So who wants to take a stab at defining what discrete means in this context? Laura.
Individual points, I guess.
Perfect, yeah. So basically like most of the times in the real world, we store things in like arrays, which are like not continuous functions. There's like a certain granularity in between every single point. So if you notice, like when we look at like a continuous convolution and a discrete convolution, there's actually, you can notice like one of the differences is this integral, which is like something that's continuous, shifts to a summation, because a summation is basically summing over a discrete amount of points. So this is a little bit more relevant to us because our images are stored discretely. It's just like a bunch of arrays containing a bunch of values. So in that case, let's, I guess, dive into what we'll actually be using for convolution, which is image convolution. So this formula is a little complicated, but I'm just going to advise you to actually ignore it for now. Basically, the process of convolution is taking like a kernel, which is in 102 speak, that's basically like, I don't know, it's like the equivalent of your step input or your Dirac delta function input. It's basically like the second thing that you're applying to an image. We often call it a kernel, a mask, or a filter. These are all pretty much synonymous for the same thing. And we have that little image there on the right, or this little like animation on the right there. The darker squares, that's the kernel. The kernel is moving around the space of the image. And what it's doing is it's actually multiplying each value of the, so basically, I think we have something that will actually pause itself on the next slide, so I'm going to come back to this one in a second. But yeah, so this is your kernel, right? And what we're essentially doing is we're saying, okay, so our kernel is 3 by 3, and what we'll do is for every single like, point in our original image, we're going to apply this kernel. So we first start with here, right? And then we apply it by multiplying all the elements in it element-wise. This is essentially discrete convolution, but on a 2D scale. We're just multiplying. So here we can see that 1 times 1 equals 1, right? 0 times 1 equals 0, 0. We can ignore all the ones with 0, right? So it's basically 1 times 1 here. Is this like too small for you guys to see? Okay, I see some people who can't see it. But basically the resulting thing that'll come out of this is basically there's a 1 times 1 here, 1 times 1 here, 1 times 1 here, 1 times 1 here. Once you're done multiplying all the elements individually, you sum it up, and that's like the new thing that it produces. So you can see that basically once you do this multiplication with this kernel, you get 4 because we had 4 1 times 1s in there. Does that process sort of make sense to everyone? Okay. So I sort of left something out, which is like the flip part of convolution in flip and drag. So what we usually do is we take this kernel and we flip it before we apply to it. So in this case, this one's symmetric. So flipping it doesn't really do anything. But when we say flip a kernel, what we mean is we flip it horizontally and then vertically, or other way around. Doesn't really matter. But yeah. Okay. Any questions? Russia.
How do you know what kernel to use?
So kernels are like tailored to like a purpose. So like some kernels will, we'll be looking at, that's pretty much the subject of the, yeah. But like kernels do all sorts of things. Like they can sharpen images, blur images, stuff like that. So yeah, we'll be exploring what people use as kernels. Okay, so I walked you through an example earlier, but let's try, okay. All right, so basically we have a kernel, right? It looks like this, and then when we want to apply it, earlier I said we flip it, so you'll notice that like this little shape of ones here, it turns into this shape because we flipped it horizontally and then vertically, and then we've applied it to the top left, right? Because we begin there. And then this returns a value, right? 3. So the top left of our resulting matrix will be 3. So, yeah. And then once we do that, because we'll move this kernel 1 over, and then we'll cover these 3 next, and then these 3. So our resulting array will be 2 by 2. Okay, so what can we do with this, right? This basically ties into your question. It's a process we call pre-processing. So one of the things we can do actually is we can do a downscaling algorithm. So a lot of the times your images will be really big and it's pretty excessive. So what we can do is we can downscale images. What downscaling images means is basically we have like an image of a certain size and we want to reduce it to a size of our choosing. So in this case we have, what is this? I swear I can't count. Okay, 6 by 6, right? And we want to reduce it to 2 by 2. So one of the things we can do is like, okay, if we want to go from 6 by 6 to 2 by 2, let's say we pick a 3 by 3 kernel, right? And then earlier we had the 3 by 3 kernel stepping through like every single one. In this case, what we can have it do is we can have it step 3 at a time, so it doesn't overlap with each other. And then that way, once you apply this filter or this kernel in this way, you'll end up with a 2 by 2 matrix. Do the dimensions of that multiplication make sense to everyone? Like the red multiplies into the red, and so on. So basically, this process is done by averaging all the pixels in the certain window that we choose. So we can do a little understanding check. So how would you go about like averaging every pixel in like say this top red window? Like what would you multiply by to get the average of like all the pixels in that window? Laura?
1/9.
Yeah, perfect. So the number of pixels in the denominator, because that's gonna average it out. So I didn't skip one, did I? Okay, perfect. All right. So what is noise? Okay. This is like, I don't know, what do they call this? Deep frying, right? This is deep fried picture of Albert Einstein. There's a lot of noise, but sometimes there is some noise that like we as humans don't really notice. Like, but it does actually in fact exist. So computers basically will localize images by looking for regions with similar pixels. So like, for instance, right, if we wanted to find a dot, similar pixels would mean like, you know, bunch of dark dots in one area or dark pixels in one area. That would be like possibly a way of localizing. But if noise is like, if all the numbers are like a tiny bit different, right? Like, shoot, I always forget, is 0 250 or is black 255? White is 255. Okay, so black would be 0 in like a conventional representation, and then 255 would be white. Let's say these pixels here were like 0, but then one of them was like 1, and one of them was like 2, and one of them was like 5. You might not be able to notice it by looking at it visually, but the computer will see like, you know, I'm not actually recognizing that these dots are all similar because you know, they're numerically different. So what can we do, right? We want to minimize the variations in individual pixels, right? We don't really want the computer to see like, oh, 0, 1, 2, 3, these are like all different. They're all pretty close together, so they should be considered as such. And then we also want to preserve some things like variation from foreground to background. So like our dice right there, right? It's we consider that as humans to be foreground, and then the background of it to be background, or like, sorry, the table to be background. So how would we go about doing this? So one of the things we can do actually is we can represent images in grayscale. So grayscale is basically 0 from 255, and it represents various shades of gray. So 0 is black and 255 is white. So if we do this conversion, we see that one of the things we've done is there's only 256 colors now, from 0 to 255. There's no red, green, and blue anymore. So we've minimized variation, but we still preserved, like, you know, you can still tell that the dice is the dice and the table is the table. So this is a pretty good thing to do. So the question is this enough? No. So let's take a look at this image, right? If we zoom in on this edge, which to us as humans looks like an edge, we can see this, right? The computer will see this. This isn't very clearly defined, and if we do something like, we say like, okay, like pixels above, I don't know, like 50, we'll color red, and then below 50, like we'll color like white or something like that, right? The computer will see something like this. This isn't a very clearly defined edge. You can see how this might be a problem because like, I don't know, you guys know how in like Microsoft Paint, like if you like draw like a circle, but it's like not together at the very end and then you use the fill function, it'll actually like flood the entire thing. Like this isn't a clearly defined edge, so we don't want this. So what's one of the things we can do to solve this? So another algorithm we will explore is blurring. So blurring typically sounds like a pretty negative thing, like you don't want a blurry image, but in this case it's actually pretty helpful. Because if we blur it together, we'll actually see that like when we look at colors that are, or when we look at pixels that are of a similar color, the edge will become uniform. So it'll actually assist us here because there's a more clear, at least to the computer, a more clear edge. Does the intuition behind that kind of make sense? Any questions? Okay, so we talked about this earlier, right? But this is how we'd go about averaging every value in in a filter. We'd multiply it by 1.9, right? It's only that in the previous example, where we downscale something, I mentioned that like instead of stepping 1 by 1 by 1, you would do a full step by 3 so it would overlap. That was sort of what was causing the downscaling. In this case, we're still walking it 1 by 1 by 1, so that's why the blurring is happening instead of the downscaling. So in this case, a box blur is basically where we apply this uniform value across every single pixel, and then we convolve this across the entire image, one step at a time. So there's a formula here, but basically the idea is you divide by the number of pixels you have in the box. So there's a question here, why don't we just fill the grid full of ones? Does anyone have any idea? Roshan?
It's not normalized.
Yes, perfect. Like you wouldn't really be blurring the same image. Your image would like raise in intensity actually. So yes, we would want to normalize it. So another example is actually the Gaussian blur. This is basically just instead of having the blur be uniform, we apply the kernel in a way such that like it models the Gaussian function. So the further away you are from the center, the less contribution it actually has to the average. So hopefully you guys have seen like this function before, but we won't be going into that like mathematically because there's a function you can actually just use to implement this. Okay, so we talked about how this will help remove noise and stuff like that. In this case, I just want to show you that like if you compare this with the downscaling one, you see how like this red and blue correspond to ones that are actually further apart than the downscaling one where it's just a 2 by 2. I'm just reinforcing the fact that like your step size, like how much you're moving the kernel by, actually does matter in this case in your end output. So yeah, but that's any questions, because this is stuff you've seen before. Okay.
Okay, so what if we wanted to simplify this even more? Too many colors. So before we were using grayscaling and we got 256 unique pixels. Is there a way that we can have only 2 unique pixels? Any ideas? Yes.
Black and white.
Yeah, exactly. So we can make our image, make every pixel black or white, so that way we have less color variations, and like Justin said, we still have the preservation of the foreground and the background, so we don't lose too much information, and the image is a lot more simplified. So how thresholding works is we have, for every pixel, we see if it's greater, so we set a threshold, like a number, and if the pixel's like darkness or value is greater than the threshold we set, then it will be pushed to be a white pixel, and if it is less than the threshold we set, then it will be pushed to be a black pixel. But there's a problem with this. Okay, so this is an example of how it would work. These are like different threshold, or this is like a good threshold, 120. Foreground, background, pretty good. So our thresholds right now are constant, and there's a problem with this. Do you know what it might be? What happens if we change the lighting of the image? If we change the lighting of the image, like make it a lot brighter, and our threshold doesn't reflect that, then our image will lose the foreground and background. So we lose information that's helpful. Oh, I think this is.
Oh, okay, yeah.
Okay. So something we can do is adaptive thresholding. So it picks the threshold number is picked based on the image itself. So like if it's a darker image and it's the average, it'll make the threshold different. There's some pros and cons to this. So for simple thresholding, which is when it's a constant value, the calculations are faster and we have more precise control about what the threshold is, like the number itself. But adaptive thresholding, it is able to sense like It handles different environments well and different lightings. And so, yes, simple thresholding, not good for environmental differences, and adaptive thresholding is slower. Now let's take a step back. So far we've been filtering by intensity. This is the grayscales basically. So this is what color looks like, this is intensity. Usually color isn't important, or I guess it could be, but what if color is important? Then what should we do? So I think you learned like there's RGB, like red, blue, green. It tells you the values for how much red, how much blue, how much green. Another way we can represent color is HSV. So hue is the color of the pixel, so if it's like red or blue. Saturation is the amount of color, so like if it's really red or if it's not so red. And value is like the brightness, so like how dark it is, how close it is to black. And 255 would be like just the color itself. Oh, yes. So in OpenCV, RGB triples are separated into distinct values, and HSV represents colors as just one value, so it's a lot easier to filter. We can use HSV when the foreground colors are very different from the background colors, kind of like, yeah, if you had like an image, like a sign or something, and against a different background, like a stop sign against grass. We can use, yes, so we can use this one, grayscale. We can use grayscale when the colors aren't as useful, but if it is, then we can use HSV. So when we use HSV color scale, it's important to blur the image first. Then we find the correct hue range. So usually you can use an online color picker, so you can see like, oh, this is the value for green, or the green that you're looking for. And then we like keep saturation for the maximum, so like we won't really be filtering by saturation value. We'll be like the allowed values are 0 to 255, but the allowed values for hue are the ones that we picked from the color picker. And then we can filter it that way. And these are some things you can do with thresholds. So you can combine them. So if you have like two, like one by green and one that's blue, then you can combine them to make the image red and blue. You can flip it, and yeah, this is like an example of masking, where it's kind of like where I said, you like, if you want to do it by color or something, and then you can put it on top of the original image. Oh, there's a better picture of this. So this is a red and blue water bottle. So here we thresholded the red water bottle, and here we thresholded the blue water bottle. So we can see that like this is like the part of the image that's chosen based on the thresholding, and then we can like overlay it on the original image and see the bottles themselves. So this is kind of like a review about the pipeline on how we process. So the original image, then we downscale, grayscale, blur, and then we threshold. This is more adaptive thresholding. For HSV, we do the original, downscale, blur, then we have the filter hue, and then the threshold. Oh, do you have questions? Okay, so we're able to like pick out the things, or how do we pick out the things, basically? So we can count the number of white regions. OpenCV will kind of do a lot of the work for you. So here it's able to see that it's like 6 circles. But there's a problem here. So we see like the normal 6 circles, but there's also a lot of tiny circles in the image as well. So we want to kind of get rid of those. So something we can do is erosion and dilation. So we shrink all the high value of the white regions, and then shrink all the low value, the black regions. So what we do is we erode to get rid of the white dots, and then we dilate to bring it back to the original size. and then we dilate to get rid of the black blotches, and then we erode to get it back to its original size. Yes. So for erosion, we were talking about kernels before. So the resulting kernel or the resulting pixel is going to be the minimum for erosion, and for dilation, the resulting pixel is going to be the maximum of the pixels that was in the little section. So if this is our original image, we can erode the white dots away and then dilate it back to its original size. And then we dilate the black dots away and then we can erode it back. So yeah, so when we're doing blob detection, it's important to do original, then we erode the white dots away, dilate it back, dilate the black dots away, and then erode it back. Okay, so we're able to get rid of all the tiny spots, but what about something like this, where it's like too big to erode or dilate away? We can notice that all the circles that we want are very circular, and then this spot isn't. So one thing we can do is we can filter by size, or we can also filter by circularity. These are like functions inside OpenCV. Other ways we can detect blobs, we can do it by the area. So that's the continuous number of continuous, well, that's the number of continuous white pixels. Colors, yeah, 0 is black, 255 is white. You can also filter by circularity, and then there's the function there. Some more fun ones are convexity. So it's the ratio of the area of like this horse to the ratio of the area of the convex hull, which is like if we wanted to encase the horse in like just like lines or like as a normal polygon. There's also ratio of inertia. So the moment of inertia when the blob is rotated around an axis that passes through the blob center. It can also be thought of as like the compactness of the image, where the ratio would be 0 and a circle would be 1. Yes. So this is erosion and dilation, and then these are different ways you can filter by like kind of like the traits of the shape. Okay. Do you have any questions?
It would be good to remember what exists on these slides when you go work on the lab, because most of it is pretty much just helping you work on the lab. But we welcome conceptual questions. That wasn't like a.
What is the benefit of eroding and then dilating before dilating then eroding? Like, if we want to get rid of some of the noisy little blobs, why do we erode and then dilate, and then we do dilate then erode?
You can do it both ways.
It strongly depends on the image. I guess we can go back and maybe explain why that particular example it was best to do. So do you like notice the tiny little white dot?
Okay.
The reason why we want to get rid of it first is if we do it the other way around, we're going to expand that tiny dot and then shrink it. So when you erode and dilate repeatedly, you kind of want to achieve something first. Like in this case, the reason why we erode first, and like eroding meaning like expanding black regions and shrinking white ones, is because we are actually given the opportunity to eliminate that tiny white dot. That means that when we eventually dilate it back, there's nothing to dilate because the white in there has actually been eliminated. So the rough idea is like there's not a particular reason why we're actually doing it this way, but just for this image, it happens to be like an effective way of doing it.
Okay, cool. Thank you.
Any other questions? Want to stop the recording, I guess? Okay, so don't forget we gave you like some extra